Thank you. I'm super excited to be here at Scalable by the Bay, and I would actually be even more excited if I could see it in real life, but that's not possible at the moment. So let's dive right in. So I'm here to talk. I'm Brecht. I work at Fauna, which is a global database. I'm here to talk about microservice patterns today, and more specifically about microservice patterns and how they might change with scalable data APIs. So the focus is really on scalable data APIs here today. Before we dive in, it's always a good idea to frame the discussion in history. And if we look at the evolution of data, in the 70s, we had traditional databases. Right after, not right after, 30 years later, in 2000, we had the NoSQL movement, and they promised scale, but at the price of consistency, which means that if you write data and you read it at multiple locations in the world, for example, or in multiple nodes, then some of these will not get the correct answer directly. So that's eventual consistency. And in that case, it might also be the application that is reading, which might make it very, very hard to write your business logic correctly. And they also did not provide relations. So it was also typically missing in NoSQL. At that time, we had an acceleration of technology. And although technology was accelerating significantly, we had databases popping up like mushrooms. It actually took quite a while to actually come to the point where we have globally distributed databases that scale, yet also provide consistency and the same consistency guarantees as you would find in a traditional database and provide relations. In 2012, we had Spanner, and a lot of people actually call that the new SQL movement or something like that. And 2 years later, we had Fauna, which also provides the same guarantees as Spanner, only it doesn't need specific hardware. While Spanner requires highly synchronized clocks, Fauna can run on any hardware. Some might call it NoSQL 2.0. I would not adopt that term because it's already a bit overloaded today, and many people are still associated with no consistency, no relations. Although Fauna is schemaless, which is also often one of the NoSQL properties. Why did it take so long? And that's a question with a very simple answer. Well, it's probably the most difficult problem to solve. And if we actually put a parallel timeline on top of that, and we look at when software service-oriented architectures and microservices became popular, and when these patterns were developed, then we are actually more or less in the NoSQL and traditional databases era. That means that most of these patterns were developed with the thought in mind that you only had NoSQL, which scales but doesn't have consistency and doesn't have relations, or you have traditional databases which might not scale. Today we are here where such databases do exist. And we can also say that traditional databases are more and more scalable today. And the question then becomes, how do these patterns change when the data layer has evolved so significantly? To answer that question, the first thing we have to do is why microservices and what motivated us to actually start with microservices. And many of us here probably, and let me quickly open the room so I can see whether questions come in. And many here will probably have the same answers as I had when I asked, okay, why should I use microservices? And those were the database layer never scales, separation of concerns, scaling in general, freedom of choice, ease of maintenance, and it actually looked very appealing. And many also turned right back and found a newfound love for monoliths when they noticed that these do introduce complex patterns, operational overhead, and eventual consistency. And it's important, since we just looked at the history, that eventual consistency was something that was considered for a long time a necessary evil. And these patterns were often developed in context of that. Today, we can make a more calculated choice. We have seen a lot of companies try microservices. We have seen them fail. We have seen them succeed as well. So we can make a calculated choice. But these choices still remain super hard to make. And that is because we miss details. Often we see something that will solve all our problems, which looks like a unicorn. And if we then start developing, we see the dragons appear. It's not our fault, by the way. That's good marketing because they're just doing their job and highlighting the positive things. And the other thing is that choosing between monoliths and microservices is actually a combination of many factors. There are lots of pros, lots of cons, somewhat heavier than the others. And what doesn't make it easier is if you choose a specific data layer, it can have a huge impact on that choice. It could tip the scale towards monoliths, but it could also tip the scale toward microservices because some databases actually offer specific features that might make it easier to adopt microservices. Or it could even make a major difference when you choose between a shared database or a database per service. So it could have an impact on the patterns you choose. One thing we can probably align on is that when it comes to microservices, and this is actually super interesting because there was a panel about microservices, so I really would love to hear your thoughts. But one thing we can probably align on is that for processing, it's a no-brainer. Microservices will help you scale up processing. When it comes to synchronization and data persistence, then it becomes very difficult. So if we look into this with a scalable data API, we first have to list a few reasons why microservices, so we can put them next to our discussion. So one of the things that we will look into is a separation of concerns and teams, independent scalability of components, which is, of course, more on the processing side, but very related to the first one. Ease of maintenance is often used as well as an advantage, and that is probably because the code remains much smaller per microservice. Freedom of choice. If you use microservices, you are often free to choose your language or your database specifically for the microservice. So specific database features that are very well suited for a specific microservice might help you a lot there. And then there's the reason that the database layer never scales or rarely scales. We can already bar because we're going with the assumption that you're adopting a scalable data API. But then you might also wonder already, if we choose one specific scalable database, do we still have the freedom of choice? And we'll address that later. So imagine we start off with a monolith, and which is often a good idea to actually start with a monolith and then start splitting up microservices as you need them instead of starting microservices immediately. And we detect a bottleneck or a desire to split off something. And in this case, it might be the user management, for example. So we'll make a user's microservice and we'll call the rest the other service. The REST service is pretty confusing. So let's call it the other service. Immediately, when you split off one microservice, you have data choices. For example, you could use separate databases per service, per schema, per instance. Imagine we take per service, then the rest would have one database and the user's service would also have one database. The advantages are that you can choose the best database for the job. It's loosely coupled. However, there are big cons as well. So cross-service joins, if needed, become a serious challenge. You might have to manage the complexity of managing multiple databases, and you will need to be able to split data. But that's often the case, that you can split data. That's usually pretty simple. But the biggest one in there is probably that you just introduced eventual consistency. If you need something from both databases, need to write to both databases at the same time, yeah, there's something you can't do unless you implement that on top of it with sagas or things like that, which we'll dive in. But the problem is that we would then move the complexity that is already solved by a database back to the engineer. The other approach, and before I go there, if you're interested in the pros and the cons of these approaches, a great resource for this that you probably already know is microservice.io. You can find a lot of information there if you want to go dig deeper. So the other approach could be one database. We could hook all services on one database. In that case, it would be ACID. So whatever transaction we do, it's the one database. So we could actually benefit from the ACID properties of the database. It would be simpler to operate, but it introduces a lot of bad things as well. Schema coupling, time-based coupling, a lot of other coupling that I didn't mention here. And you might say, okay, databases need to be scaled now. And can I still use the right database for the job? I do realize that this pattern is often considered evil for many people. And I'm not here to advocate for one or the other. I just am here to show what actually changes when the database layer scales. The first thing we can obviously already change here, if we scalable data API-ify this, and we would, for example, use Fauna, which is what I'm going to use because I know it best. Databases need to be scaled. Yeah, we can remove that one because we're assuming the database scales here. It's not your concern anymore. Simpler to operate. Well, that's an argument that is here, but that is often used. But actually, yeah, this database is indeed zero operations. It's one click to get a database, but it's also true at the other side. If you would use Fauna for both, and I assume if you can't use Fauna for both, you would have specific requirements, that there are other databases that make it very, very easy to set up a database today. In Fauna, for example, you could actually simply make databases in databases, and you can make as many databases as you want. So I would say that zero operations are the fact that it's harder for microservices to maintain these databases is not really of a strong argument anymore today. So let's remove that. But let's look at those two, schema coupling and time-based coupling, because those are the reason why using one database is often evil. However, if we look at it, why we need that, we typically need that so that two teams can work completely independently without having an impact on each other. That means that you could actually parallelize development, which is something that a lot of managers would love to hear, and that makes sense, right? If you can parallelize development, you can scale up teams more easily. But if we look at the actual thing that we are trying to accomplish here, then it's actually logical boundaries that we're trying to make. And maybe that microservice pattern of splitting up databases is not necessary here. It might be a good idea. It might be. But in this case, we could, for example, use another approach. Let's say we use user-defined functions, which is much like a stored procedure, only you would implement it in Fauna in the same query language as you would normally query. And you would say, okay, but a stored procedure or a user-defined function, yeah, you can make an API so that one team gets an API to the other service and you won't impact anything as long as you keep the API the same. But what about migrations? But there are also solutions for these. So if we combine the user-defined function and look at how FQL works, which is the Fauna query language, this is how we would create a function. And this is actually also pure FQL. So the FQL is also used to create a function. We could easily split off the logic that we're going to place in that function. Imagine that we have some other FQL that is the logic. And this is actually pure JavaScript. And basically what I'm showing here is that FQL is super composable, which is very, very useful for what I'm going to show of an approach to actually separate the APIs. If we then combine that with the security system, we could say we have one rule that says this team can call this function, while we could be making another rule that says this team can only update that function. And we could integrate it in the deploy cycle with a specific key that only can update the function and the other key can only call it. If we then go further and look at the fact that Fauna also has temporality, we could also tackle migrations. For example, we would just say, okay, the first logic is some FQL query. Second logic is the other FQL query for version 2. We will, of course, deliver the same data. And it's important to notice that Fauna is schemaless, so you don't have schema migrations. But of course, a schema does live something somewhere. And in this case, that would be in the code, of course, in the query. Then we could have migration logic again in a separate statement. These could even be in different files. Essentially, what we're doing here is function composition. And then we could actually get to our final query. And the query would simply say, okay, we get a user because we're going to do something with the user in the microservice. Then we get a timestamp. And because of the temporality of Fauna, everything has a timestamp. You can even go back in time if you would want that. And then the only thing we have to do, and this is where SQL is very strong at, like conditional logic. We could say, if the timestamp is smaller than now, then we're going to execute logic v1. And immediately we're going to migrate the data, for example, because the logic for v2 requires a small change to the data. And the next time you're going to call this on the same document, the timestamp will be updated. So you're going to automatically call logic v2. That way you could actually easily make a separation. Is that perfect? Of course not. So let's put a neutral smiley there. But what if you could actually execute transactions over multiple databases? That would be awesome, right? However, I have to disappoint you. It's actually, I mentioned it because it's feasible, but we haven't implemented it yet. The idea here is that it's time for databases to adapt to your serverless and microservices needs instead of the other way around, instead of creating algorithms to cope with the things that it can't do. If such a feature like transactions over multiple databases would be of interest, feel free to open a feature request. I don't think we have one already, although it's an idea that lives internally. Then we have time-based coupling, of course. What happens if you write to the same data? What if you have a noisy neighbor? What if you have locks? We can already eliminate noisy neighbor because that becomes the problem of the Scalable Data API. That shouldn't be your problem to worry about. If you look at Fauna for the rest, for the writing to the same data and locks, this is inspired by Kelvin, which actually does optimistic calculations. We have written a whole article on CSS if that interests you. This image also comes from there. You might say, okay, but optimistic calculations, those are just like locks, right? And therefore still locks. And that's true, but reads are not affected by these optimistic locks, which is not the case for other databases with OCC checks. And at the same time, for the writes, there are a number of optimization techniques that you can do at the database level, especially with such an algorithm. These are more questions for our engineers. If you do want to know more about that, join our community. But what is important as well is that besides of the optimizations you can do on the database level, you can also do a lot on the application level. Imagine that you have a database, a collection, and a document. And imagine you have a bottleneck in the document because many people are writing to it. At that point, you might argue that this is actually an application requirement. If you are able to split up the document and therefore able to split up your data and put it in different microservices, then basically you don't have that application requirement, and you could have split that document as well in the one database. So there are always workarounds. Imagine you have a counter, for example. You could even say, I split up that counter in multiple counters. I randomly select a counter where I would increment it and then would aggregate it at the moment I read. However, the last disadvantage here, use the right database for the job. It's true that no single database is good for everything. However, if you look at the database world, the different types of databases, OLTP, relational, document stores, search engines, OLAP, graph databases, what we're seeing the last years is that databases are growing more together. The gap between databases is changing. We have much more databases who are multimodal. And if you look at Fauna, for example, it sits around there. It's relational, it's document-based, it has search capabilities, have graph-like capabilities, is scalable, and has temporality built in. And of course, it's an OLTP database. However, I repeat, it's still true that no single database is good for everything. And there I would argue that it typically boils down to data requirements. Do you need consistency? Do you need a global database? Do you need transactions, or do you need disaster recovery? And depending on those, you would actually be able to choose then. And if you take that into account, that it depends on the data or the data requirements, maybe this makes more sense, that we have a set of services that would actually integrate on the database level, which actually have consistent and transactional data needs. In theory, it would be possible if your data layer is scalable. And then we have other specific data needs where we would actually have a database per service, for example, in case there is a database we really need for a specific service, but it doesn't scale, we could always take a different approach there. Or actually combine the two if a service needs data from both. An example, if we would only combine two databases, and we're taking two scalable databases here, Fauna and Rockset, we would have all these possibilities already. So we would have a database that's relational, document, graph-like, temporal, and ISO LTP database, where we could actually do the bulk of our data operations that need consistency and need our data to be safe. And then we could use the temporality features, for example, to pull out change sets and actually stream the rest to Rockset, which brings you with real-time analytics search engines and OLAP. So we have looked at one side. In the other side, if we would have separated database per service, we would have the advantage of loose coupling, but we have the disadvantage that cross-service joins is a challenge. So we did that because we want our teams to scale independently. Even there, a database or specific database features could help a lot. So what if service one needs data from service two? There are multiple ways you could actually make that happen, even if you have a database per service. You could have transactions in the microservice. You could merge a microservice again, but yeah, that doesn't make sense in this case because we just split it off. We could have asynchronous messaging, or we could actually have a materialized view. So the second service could have a materialized view on the data from the first service. I would already bar this one because we split it off. We don't want to merge it again. Then transactions in the microservice, that's a very strange idea. It's very similar to the Saga pattern, but in essence, what you're doing is placing the problem which has been solved by the database again in the engineer's hands, which means you're going to spend a lot of time on something that databases have spent years and years to try to solve for you. Of course, these two are still a very, in my opinion, because this is an opinion, of course, are still very good options. And let's go back to the same idea as before. It's time for the database to adapt to your serverless and microservices needs. And for these two, that means Fauna could, for example, help you with the temporality. That means it enables change data capture. It enables the easy implementation of a queue. You could do CQRS without actually setting up a different queue infrastructure, I mean. And soon we even have push-based streaming, which would actually get real-time data into another system in a push-based fashion. So we could say that cross-service joins is a challenge, but we can get a lot of help from the database there as well. So let's put a neutral phase there. And once we then put these two together, I would argue that it typically boils to the database. Typically the choice between microservices and how you would implement it, whether you would stick with a monolith, whether you would go to microservices, or how you would, which pattern you would choose if you go to microservices, purely depends on what data requirements you have. Are you able to split up your data? Perfect, go for it. Do you accept eventual consistency? That's already something you have to think through, because often the issues with eventual consistency are only apparent after your application starts to scale. And then can you find workarounds for the time-based coupling? And do you want to use a different database for a specific microservice? So my goal here is to spark a discussion and actually hear what you have to say about this. Like, how do you do it currently? And I want to spark a discussion about the fact that databases have made huge leaps in the last 10 years. And do we still think the same way about microservices, or is that changing? Are you already changing your patterns? The idea here is as well that it's time for databases to adapt to your serverless or microservices needs instead of the other way around. And when a database actually scales and is consistent, the trade-offs change significantly. Therefore, it often depends on data requirements. So, and finally, choices like whether you need database sharing or whether you're going to adopt a non-sharing principle and start a database per service could actually be different per group of services. It's not because you decide that for one particular set of services, going to have a database per service, that you have to do it over all the services. It might actually depend on what service needs what. These are the actual ideas that I wanted to convey today and have a discussion about. So I hope there are some questions in the Q&A after this. If you're interested in how Fauna could help you implement microservices, you can actually try Fauna for free. We have a pretty large free tier. So in that case, go to fauna.com. And if you have questions, join our community at community.fauna.com.